Welcome to the Beals Science School. We're going to dive into the quantum world. If you've been following along on a lot of these lessons, we've been looking at light as a wave, as a particle, as a photon, as all these different things. And to truly understand the next step of light, we need to understand the quantum world and what that means. And this is where things get really strange, but they also get really exciting. Let's start off with quantum mechanics. Quantum mechanics is a mathematical description of the motion and the interaction of subatomic particles. What is subatomic? Sub means smaller than or under atomic. So that's all the things that are smaller than an atom, that make up an atom. Now, interestingly, it's based only on mathematical probability because there's a problem. The problem is, how are we supposed to see quantum particles? How are we supposed to see things that are smaller than an atom when we really can't even see the parts and pieces of an atom? Well, we can't see them, but we can understand them mathematically and try to build a visual picture of them based off of the math. That's where this actually gets really challenging. And the Heisenberg uncertainty principle helps us understand this. The observer effect of the Heisenberg uncertainty principle says it's impossible to know the exact speed and position of a subatomic particle. For this, we're going to focus on electrons. There are lots of subatomic particles, but we're going to focus on one that really matters for what we've been learning about, and that's atomic theory. So here's the thing. If we want to know where an electron is around the outside of an atom, the only way that we can observe that is to use light. Basically to shoot photons at the atom to try to figure out where the electron lives. But here's the thing, and we just learned this in the last lesson, which is the photoelectric effect. And if you're not familiar with that, there's a link down there that'll take you back to the other lessons and get you caught up. But here's the thing, if an electron absorbs energy, like light or photons, it absorbs that energy and it moves to a new spot. It jumps to a different energy location. Which means the very moment that we find an electron using light, it disappears from that spot. So we might be able to see where it was, but now we don't know where it went. We've lost it. That's the uncertainty principle. So here's the thing. It's impossible, as we said earlier, to know the exact speed and position of a particle. But let me try to help you make sense of this. Now, I need you to pretend with me here for a moment, okay? We're going to pretend an electron is a balloon. We're going to blow up a balloon. And then we're going to let that balloon free in the room that you are currently in right now. And then we're going to need to set up some fans so that the balloon floats around in the room. It's moving because electrons are always moving. And all I need you to do is set a timer for every second. When that timer goes off, you're going to make a little, you need a little map of the room. Maybe you're going to make a dot on the map where you saw the electron, or not an electron, where you saw the balloon. And all of a sudden, you might have lots of dots in a certain area. But here's the thing. That's a oversimplification because we can't see electrons. So let's make this a little more realistic. I'm going to turn all the lights off, and I'm going to give you a flashlight. Now, with the flashlight, you could shine it around the room, right? And you could keep track of where the trouble is, and we just talked about this. The second the light hits an electron, if we're going to pretend that our balloon is an electron, the second the light hits the electron, what happens to the electron? It absorbs the energy, it disappears from that spot, and it goes somewhere else. So let's make this even more realistic. We're going to take the balloon, we're going to set it free in your room full of fans that are blowing around. That balloon's going to go all over the place. And then I'm going to turn all the lights off, and then I'm going to give you flashlights to throw. Just like if you were throwing a photon or shooting a photon to try to find the balloon or try to find the electron. And you're just going to throw them around the room. And everywhere you throw them, every time you hit a balloon, because it's going to move the balloon as soon as you hit it, you're going to make a little dot and you're going to build a map, right? This is my room right now if I shut all the lights off. And if I set a timer for every second, I would just make a mark wherever I find that balloon at any given time. So let me try that. I'm going to spend a whole bunch of time making a dot as I chuck this thing around here. And when I come back, you're going to see a lot more dots on my screen. I've spent maybe an hour, and this is all the places in my room that I've actually bumped into the balloon floating around. In other words, these are the places that it keeps tend to hang out, but I don't want to stop yet. I'm going to keep going. I'm going to let the balloon float around the room. I'm going to keep throwing flashlights. Remember, my flashlights are like photons, and I'm just trying to build a map of where the electron is at any given time. So I'm going to keep going, and everywhere I see that thing, I'm going to make a dot, and I'll be back in a moment with more dots. So more time has passed. I've been throwing photons all around my room trying to find that electron, and I'm still making more dots every time I bump into an electron, but I'm going to keep going. So a whole bunch of time has passed. I have been throwing photons, or flashlights, around my room to try to hit electrons that are moving around, or the balloon is our analogy. And every time I did, I put a dot on the screen. Now, interestingly, it looks like there are areas up here where I did not encounter the balloon very often. And there are areas where I ran into the balloon, or I found the balloon. It was spending more time in those areas than it was in these, because remember, I'm just randomly trying to find it, which means it must be hanging out in these areas more often than it's hanging out in these areas. Why is that? Well, I don't know. Maybe it's the way I set the fans up in the room. Maybe it's the way my room. But here's the challenge. Here's what I'm going to do. I'm going to give you the option to catch the balloon. So remember, it's still completely dark in my room. Completely dark. The fans are on. And I'm going to give you the option to go somewhere in my room and catch the balloon. And if you catch the balloon, I'm going to give you a $100 bill. Well, isn't that nice? Now, here's the thing. Are you going to hang out right here and say, I think I will catch the balloon right here? Probably not. You're going to say, well, this looks like a spot where the balloon hangs out quite a bit. This is, yeah, these areas, like, I don't think I should hang out there. I think I'm going to plop myself right in this part of your room so that I can catch that balloon when the lights come on, because it's going to be right in that. I'm going to catch it, and I'm going to collect my $100. That's what probability is, right? You have just answered the whole question that you don't know where the balloon is going to be. It could be anywhere in any of these areas, but you've chosen to go to an area where the balloon spends more time than anywhere else. So even though you don't know where the balloon is, you have a good idea of where it tends to hang out. This is exactly how we build a picture of an atom. We don't know where an electron is at any given time, but we know where electrons tend to hang out. And this is a huge part of our understanding of what an atom actually looks like. But we have to understand the quantum world, and we have to understand where electrons tend to live, just like where does our balloon spend more time in the room? And if we take that and we expand it even further, and let's say we just continue to throw flashlights over and over and over, we might get a picture like this, where there's literally dots in some areas, and those areas have so many dots it looks like they're almost white, and other areas don't hardly have any dots at all. This shows us the areas where electrons are hanging out around the outside of an atom. Even though we can't see the individual electrons at any given time, we can figure out where they spend most of their time. And this looks very different than the Bohr model of the atom, which is something that we've explored in the past. If we do this a whole bunch, which scientists have, they've done this with atoms to figure out where do electrons hang out around the outside of the atom, and we get these crazy shapes that form. But this is far more realistic model of the atom than the nice little model, and I'm going to remind you of it, that's called the Bohr model. Now look, that doesn't mean that atoms are in that. It just means that atoms tend to be found in that ring. That'd be a really good place to hang out if you were going to try to catch an electron. You wouldn't want to hang out right here if you were going to try to catch an electron, because no electron is hanging out there. Well, let's put this all together and try to make sense of it. This whole big thing is called the quantum mechanical model of the atom. We've drawn Bohr models in past lessons, and what we said was this is a good representation. It's a good way to look at an atom, and it is useful. In fact, we're going to use it as we go forward in chemistry. But an atom where the electrons live looks a lot more crazy like this over here. So the quantum mechanical model, and I would write this down if I was you and taking notes, it describes electrons having both wave-like and particle-like properties existing in regions of probability that we call orbitals. Now think about this. Each one of these areas is just mathematical probability. When electrons have been studied around the outside of atoms, this is an area where, in this example, they tend to be found. That's an area you would go back to if you were going to try to catch an electron. So it's the probability. And these, all the little dots, make these fuzzy areas that we call electron clouds. The orbital then, which we saw right here, another term for it is an electron cloud. It's not a real cloud, it's just an area where there's a whole bunch of dots that a scientist put on the screen because they kept on encountering electrons in those areas. It's a high probability of finding an electron in that spot. And if we look, there's very specific areas where electrons live. In fact, there are different energy levels where they live. Their orbits are not circular like planets around the sun. They're just kind of spending time in these very different areas. So different than the Bohr model on the last one. And here's the thing, we could go hang out right in this area. It doesn't mean we're going to find an electron. It's just a place where there's a high probability of finding an electron. It spends time in all of these areas. Now this looks all crazy and messy and weird, but I promise we are going to make sense of it. And in the next lesson, we're going to learn what are those shapes, what do those different electron clouds tell us about the location where electrons live. We're building up to bigger things. We've started all the way with learning about electrons and how they make light, and now we're in the quantum world. And next we're going to go in and we're going to find out, wow, we can actually write these crazy codes using orbitals and show the exact location of electrons around the outside of atoms. So stick with me, that's coming up next, and keep on learning.